Today we start talking about chapter 17 of the book dedicated to the introduction to boundary layers. If we have enough time today, we also can start chapter 18 dedicated to laminar boundary layers. Please don't forget to ask your questions in chat or ask by voice. Today I can see our chat, so we can communicate if you would like to ask some question. Okay, presence of boundary layer can be observed on experiment, and quite evident that in many cases this effect of such a process of fluid and solid body interaction is important to take into account. Through boundary layer, we have transformation of forces from flow energy to forces on the surface. And also we have heat transfer, which in many practical cases is important to calculate, especially for the flow in high velocity, supersonic velocity or hypersonic velocity. In such case, heat transfer is significant. Chapter 17 is divided in two parts, which are boundary layer properties, where we study velocity and temperature profile, shear stress and heat transfer, boundary layer thickness, displacement thickness, momentum thickness, laminar and turbulent flow definition. And second part devoted to boundary layer equations which we use to solve flow pattern around the body to determine velocity profile and temperature profile. Boundary layer properties. Once we talk about high velocity applications, compressible flow, we can see both changes of velocity and temperature. Velocity profile determines the thickness of boundary layer, and temperature profile determines the thickness of thermal boundary layer. How we understand that the concept of thickness of boundary layer? We must compare velocity on infinite, V infinite, and velocity on each particular point. In case when velocity outside of boundary layer happens, it is equal to infinite velocity or external velocity, denoted here on figure 3 as UE. Everywhere where velocity is smaller, U smaller than UE, external velocity or edge velocity, we have flow inside boundary layer. In real application, not always possible to make such a rigid comparison. So we have some tolerance, usually from 1 to 5%. We can say that if our velocity would be at any particular point inside the boundary layer equal to 0.95 to 0.99% of external velocity, we have edge of boundary layer. So due to fluctuations, due to unsteady processes, due to presence of free turbulence inside flow, we always have variation of velocity in each particular point. So typically, once we analyze flow pattern, we can determine that when velocity reaches from 95 to 99% of external velocity, we reach edge of boundary layer. And there is also a boundary layer associated with change of temperature. Due to heat transfer process, temperature profile also happens. As you can see on figure 3, there is a typical temperature profile where on the wall flow is cooler near the wall, right? So temperature of the wall is smaller than temperature of flow, and there is temperature on the edge, TE, of thermal boundary layer, and in the middle we have variation of temperature. Temperature increases due to viscous interactions in this direction. Temperature increases once gradient of velocity rises. Velocity transforms to heat. So temperature inside flow increases. There is some point at which this temperature due to energy exchange becomes maximum. Okay, and then due to cooling of flow in cooling of flow between gas and solid, we have drop of this temperature. There are several profiles, typical profiles which we could observe. This is one of those profiles. Others we will see soon, talking about laminar and turbulent flow very soon. So some of these possible profiles is shown on figure 3, but it's not the only profile which can happen in real flow. Velocity profile, which we also see here, is quite standard, right? We know it from long time ago, even from previous disciplines, that velocity on the wall is equal 0. All velocity components to solve flow equations. We know that at this point we have u equals 0 and v equals 0. And then velocity increases till the edge of boundary layer. Theoretically, outside of boundary layer, velocity will be already high and close to infinite velocity, at least in case of this task of flat plate. Due to temperature difference, we have also heat flux. QW is a heat flux on the wall, right? Probably it's defined as watts per square meter, typical units, right? And due to presence of velocity gradient, we have shear stress, tau W, on the wall, maximum shear stress on the wall, because gradient of velocity has its maximum on the wall. Okay, so once we see theory of boundary layer, we see not only velocity profile, but also temperature profile. As we already saw from chapter 15, there is a relation between velocity and temperature, right? Or velocity distribution and temperature distribution, because inside shear stress function, we have viscosity or dynamic viscosity, which is a function of temperature. Soon we will see these temperature functions once we solve equations of laminar and turbulent flow. Some function we already saw, I think, on the previous slide. Here are the functions, relation between shear stress and velocity gradient, equation 1, equation 2, relation between temperature gradient and heat flux, proportional to conductivity. It's a conductivity coefficient or heat transfer coefficient in this case, I think. And another property is to quantify the boundary layer, velocity, thermal boundary layer, and others, is so-called displacement thickness, presented here, delta asterisk. What is the displacement thickness? There is no image. Okay, I will draw you on the side. Once we see a balance, for example, balance of mass, we have a profile of this mass balance over the cross section, and this balance of total mass flow rate, which we have due to presence of boundary layer, is not maximum possible. For example, we can compare this with the flow without boundary layer and with boundary layers. Let's have one example. I will have, just a moment. I will have a wall and a boundary layer on this wall. For example, starting from this point and growing this boundary layer. On this boundary layer, I will draw a profile of velocity like this. Okay, and I will have, for example, edge, which describes the symmetry axis. Due to presence of boundary layer, we have a velocity profile distributed in such a way that is inside boundary layer. Velocity is not constant, as we know. So amount of mass which could pass without boundary layer is bigger. If I draw here by another color, calculation of mass flow rate without boundary layer, I would assume that my velocity would be constant everywhere, independently on the distance from the wall. So this mass flow rate calculated when we do not take into account presence of boundary layer is shown here on equation B. Is hypothetical mass flow rate between 0 and some coordinate y1. This is coordinate y1 here, where boundary layer is not present. How we do it? We multiply density by velocity and integrate. Once this velocity is constant, we can substitute by just a product. I will write here that this is density multiplied by velocity and multiplied by y1 coordinate. This is bidimensional case. It's not three-dimensional. It's bidimensional case. So my area is equal y1. Okay. What is rho e ue? Flow properties of on the edge of boundary layer. Okay, they happen here on this line of constant value. We have rho e and ue, density and velocity. For incompressible flow, density will be constant everywhere. For compressible flow, density will be also variable and will not be constant. So this is why we're writing rho e and ue, not just velocity by itself. This is hypothetical maximum possible mass flow rate which we would have if boundary layer does not exist. But in real flow, boundary layer exists. So instead of integration of product of density and velocity, rho e and ue, we must use actual values, rho and u, in each particular point. So relation A is given to us this value, mass flow rate calculated by real values of density and velocity distribution along coordinate, along normal coordinate. Okay, this is our axis y. And this is A. Once we subtract B from A, we will obtain such a difference of mass flow rate, which the mass flow rate which we do not, let's say, we do not have, which we miss due to presence of a boundary layer. And this mass flow rate difference would be proportional to this area here. I will mark with the blue color. So this mass flow rate and this velocity, which we do not have inside the real flow, this is what we are missing. once we subtract these two quantities and we can rewrite mass balance, we will obtain that, just a moment, here. We will obtain that thickness inside which theoretically we have zero flow. Where is it? Where is it? It's not, the image is not here, so I will draw you another image which corresponds to these formulas here. Okay, this is my wall. Okay, some axis, flow profile, boundary layer finishes somewhere here. So I will show you exaggerated boundary layer, very big size boundary, very thick boundary layer. Okay, real velocity distribution. And now what was written in the formula, I will make in a graphical form. I will present in a graphical form. So with another color, I will, okay, let me make a bit small modification here. Everything what is inside this red zone, inside this velocity, I will substitute by a rectangle. Okay, something like this. Okay, probably like this. So this area here, inside this zone which is missing, I will put here. Okay, so this area 1 and area 2 would be equal. A1 and A2 is equal to A1. So I just replace some function. This is a function of density velocity product. Okay. And what is missing here is zero value. Since I already remove all from velocity to the upper zone inside the area 2, I will have zero value of velocity in the remaining part. So this zero velocity zone is denoted as delta asterisk. This delta asterisk is theoretically zone where flow does not happen, when there is no flow. And this zone can be calculated mathematically when we write the balance of mass in profile of a boundary layer. How is it written? Mass flow rate, which is missing, is the difference between mass flow rate B and A from our previous, okay, B minus A. Mass flow rate flow difference is the difference between hypothetical mass flow rate where a boundary layer is not present and real mass flow rate. Okay, this relation you can see on the right side of this function here. And then dividing left and right side by product ρe UE, we obtain equation 6, which gives us analytical definition of delta asterisk. This delta asterisk is the zone or thickness where flow does not happen. Okay, and this, when we are calculating in C units, also will give us dimensional value of displacement thickness. As you might see from this function, once we analyze this function, we will see that delta asterisk would be smaller than delta. It will be always smaller than thickness of boundary layer due to this area relation, right? And usually is there is a recommendation that delta asterisk is very close to 0.3 delta, the first estimation which we can use to calculate this displacement thickness. What does it give to us in practical applications, this definition of displacement thickness? Is the following. Let's go here. When we see a presence of boundary layer, okay, right side of figure 5, streamlines will be always displaced with respect to inviscid case. We'll always have inclination which would correspond to this delta asterisk displacement thickness. Is because due to presence of boundary layer or all external streamlines, they are curved outside of boundary layer, and they are curved exactly on the angle of delta asterisk. So once we are capable to estimate this displacement thickness, we can evaluate direction of streamline outside of boundary layer. It's one application, and another application is the following, that it is possible to calculate, let's say, some effects of viscous flow without actual calculating a boundary layer. If we substitute some real body surface by another body, which we call effective body, where we add in each point of its geometry this delta asterisk displacement thickness, is the thickness where flow will not happen. Okay, so where mass flow rate would be equal to 0. We remember that mass flow rate going on thickness of displacement is equal 0. So our actual body will be thicker and will become effective body, and outside of effective body flow will be same as for inviscid case. We can change the surface size and use inviscid model to calculate flow around this body. This is very typical approach, which was used from long time ago when simulation of boundary layer was not possible, and by substituting actual body with effective body, we could use inviscid flow equations and calculate quite precisely behavior of the flow. Of course, this method has disadvantages because without real calculation of boundary layer, we do not see this profile, right? And we do not see shear stress, we do not see many other things. But we are relatively simple and relatively fast can calculate flow with taking into account some effect or curvature of flow due to presence of boundary layer. So this is calculation of viscous effects without calculation of boundary layer. Some kind of compromise between accuracy in physical simulation and let's say performance of this calculation. Displacement thickness is not the only parameter which is considered in viscous calculation. There is also another parameter which is called momentum displacement thickness, which is similar to the displacement thickness. So momentum displacement theta is defined also by similar consideration. We have two momentums. One momentum created by flow without boundary layer is B. Okay. Another momentum created by flow with boundary layer, which is A. And then difference B minus A gives us decrease of momentum or decrement in momentum associated with the presence of boundary layer. So in such case, this displacement of momentum can be calculated. Displacement of momentum is also dimensional parameter, and it will have dimension of size or space. Okay, some considerations, some conclusions from this. One conclusion is that the displacement momentum would be proportional to friction coefficient, as we might see on the last equation. Proportional, but not equal, of course. Bigger is the friction coefficient, bigger is the displacement of momentum. And these parameters allow us to simplify flow, or to simplify calculation of flow in a preliminary phase of design. Next paragraph we see is devoted to boundary layer equations. What are the boundary layer equations? They are flow equations, for example, Navier-Stokes equation system, with several simplifications. Main simplification in boundary layer equation is that size, which is delta, thickness of boundary layer, is significantly smaller than size of the body. Delta is much smaller than C. With these simplifications, we can reduce complexity of flow equations. I will not show you how it's made. We will leave it for your personal study if you want. And this is explained very nicely in our textbook, and also in computational fluid dynamics and heat transfer, where this transformation is made. All steps are described in a whole chapter of a book of computational fluid dynamics and heat transfer. Here I would like to show you the final result of this transformation from Navier-Stokes equations to boundary layer equations. You can see that it's a bidimensional case. We have only x and y direction. It's a stationary case. We do not have time derivative. And the continuity equation is the first, equation 28, remains the same for external flow and flow inside boundary layer, because we have conservation of mass always working. Cannot simplify anything inside mass conservation. But in momentum equation, we can significantly simplify y momentum, or momentum on y-axis, which tells us that to correspond to boundary layer equation, the momentum equation on y direction would be simply derivative of pressure, or derivative of pressure by y direction would be equal to 0. Once we will try to visualize distribution of pressure on the boundary layer, I will make a small schematic. For example, we have again our plane with, where is it? Here. With a boundary layer inside. This is boundary layer, and for example, we have supersonic flow, or flow with shock wave. Okay, let's see here. Shock wave is represented by pressure gradient, right? So pressure lines, or constant pressure lines, are very close here inside. Once you calculate or simulate with these equations behavior of a boundary layer and such interaction, you will see a very interesting picture is showing that flow distribution would be like this. Okay, so pressure distribution, it's these lines will correspond to different pressure levels: pressure 1, pressure 2, pressure 3, and etc. This is how we can always understand that we deal with viscous flow. Once we see simulation of viscous flow and behavior of pressure inside boundary layer, for viscous flow, this behavior of pressure will have always normal direction with respect to the wall direction. So pressure lines will be always perpendicular to the wall. Okay, if we make same simulation but for inviscid flow, we will see that pressure lines will be not normal, will be inclined. Okay, something like I will try to show you. Okay, this is our shock wave. Okay, this is the wall. This is our shock wave. A lot of lines because it hits the surface. Okay, and then it reflects on the surface, from the surface. So these lines are not perpendicular to the wall. So once we see this figure, we understand that the boundary layer was not simulated. Once we see figure on the top where pressure lines distribute to normal on the change direction to normal with respect to the wall, we understand that this simulation was viscous. Okay, viscous and inviscid. Okay, viscous and inviscid flow. Energy equation is also simplified in bidimensional cases. We might see on equation 31. To complement with or to complete system of equations, we have also continuity and the enthalpy equation as usual. To solve this equation system, we must set boundary conditions. On the wall, we have 0 components of velocity, u and v components of velocity on the wall, y equal to 0. And boundary condition related to temperature. As we saw on our previous lecture, it can be constant wall temperature, it could be 0 temperature gradient, or it could be known heat flux on the wall. Okay, QW could be dt by dy equals 0. So one of those 3 boundary conditions could be implemented in different computational software, including ANSYS Fluent. And another boundary condition we set on the edge of boundary layer. This equation system works only on inside the boundary layer. So theoretically, boundary layer would finish on infinite distance from the ball, because as I said, we have always variation of velocity. Okay, it's continuous process, but we will limit, right, by 95, 99% of velocity. On this edge of boundary layer, we have velocity equal to external velocity outside of boundary layer, which is close to infinite velocity. And on the edge of boundary layer, we must also set condition for temperature. It could be known temperature on the edge of boundary layer. Once we solve all inside the program, like in ANSYS Fluent, these boundary conditions will be set automatically. And as you will see, as you can find from the book, sometimes, or let's say differently, often, these boundary layer equations would be more generalized to be used not just inside boundary layer. Instead of these simplified equations would be solved complete equations of Navier-Stokes inside the boundary layer and outside boundary layer. How do we solve? I think it's obvious that we solve boundary layer equations by CFD, computational fluid dynamics. It's the end of chapter 17. Please ask your questions, and meanwhile I will open topic 18, chapter 18. Just a moment. Please don't forget to ask your questions. I will start chapter 18 today. I would like to do it because there would be time for you, some free time, where we will not have classes when we finish this theory. So you will have more time to prepare reports. This is why I want to finish sooner. Okay, this is chapter 18 or part 18 of gas dynamics devoted to laminar boundary layers. Here in this chapter we will speak only about laminar part of boundary layer or laminar boundary layer by itself, which is characterized by a specific flow profile. Okay, here is the roadmap for chapter 18. We call about classical solutions. Laminar model can be solved in simplified form for incompressible flow for flat plate and for compressible flow for flat plate. We could also talk about stagnation point and reference temperature method. Advanced method to calculate compressible flow boundary layer in a laminar regime, and some topic dedicated to CFD method, finite difference method applied to laminar flow. I think today we will just make the left part, and probably next time we will talk about CFD and start the next chapter. Let's see how it goes. For now, I see no questions asked in the chat, so probably I can continue. Laminar boundary layer. Simplest case is laminar boundary layer on a flat plate, so-called Blasius solution. Here is the equation system for a flat plate. Equation 1, 2, and 3. Equation 1 is a continuity equation. Equation 2 is momentum on x direction, and equation 3 is momentum on y direction. No energy equation. Probably you know that since density is not present inside this equation, it means that density is constant is not included inside this system. Here there is nu, which is viscosity, right? Calculated by a ratio between dynamic viscosity and density. It's cinematic viscosity. To solve this equation system 1, 2, 3, we must provide transformation of coordinates as shown on equation 4, 5, and 6. Equation 4 defines two new coordinates. Xi is equal to x. It's just formal substitution of coordinates. And eta is a combination between normal direction and longitudinal direction of coordinates. Then with the transformation of coordinates, we can obtain coordinate system, equation, which is identical, not identical, okay, which is equivalent to that equation system. This transformation is done step by step. I just put here all these formulas in a sequence from one formula to another, how it goes. So for example, definition of derivatives, right? Complex derivatives on x and y direction, second derivative for calculation of viscous part. And also these equations involve in some way stream function C. We know that stream function is also related to velocity component. Here we can see this relation, and with previously defined function, we assume that stream function will correspond to the following form that is shown on the screen on the left. Here function f is representing to us sort of integral of dimensionless velocity, where f prime derivative of f function will be velocity ratio. So it's dimensionless velocity. Substituting this definition in inside function 12, we will obtain that relation on velocity, which could be used for flow equation. Then same we do with v component of velocity here, which would be derivative of stream function by x direction, negative. Okay, taking all previous definitions, we obtain this v component of velocity inside equation 13, and combining inside the flow equation, going back, putting all together, we obtain equation 15. Equation above 15 is same equation with just with parameters not simplified, right? And equation 15 is simplified version of previous equation. So this simplify. You know, I like to work in mathematical software, especially in Wolfram Mathematica when we have possibility. And there is a special function in Mathematica which allows us to make transformation analytical of an analytical relation, not just to provide numerical calculation, but also has very powerful analytical apparatus. And there is a function there, simplify. Once you apply the simplify function to function above, you will receive equation 15. Very significant transformation. Equation 15 consists of just function f and derivatives of function f. This part here is a third derivative. It's an ordinary derivative of function f. This is second derivative of function f, and this one is function f by itself. Okay. And this differential equation, ordinary differential equation, is extremely simple and can be solved, unfortunately not analytical, but it can be solved numerically. For example, by method of Runge-Kutta. This equation 15 is called Blasius equation. Blasius was a doctorate student of Prandtl, and it was long time ago, around 80, 90 years ago. So Blasius developed from a theory of Prandtl this equation, and since it's simple, it was possible to solve it not analytically, sorry, with simple numerical method by hand. Okay, and such solution is called Blasius solution. To solve this equation, Blasius equation, numerically, we must set boundary conditions. Boundary conditions are the following. At eta equals 0, where eta is here defined as, okay, let's see, eta equals 0 means that y coordinate is equal 0. Or we can write vice versa. If y coordinate is 0, eta function will be equal to 0 independently on x coordinate, except x, no, also for x equals 0 probably. So we are talking about the wall, this first boundary condition. Eta equals 0 is the wall. it means that velocity on the wall F prime would be equal 0. So it's V equals 0 is equivalent. Okay, and F equals 0 is giving to us streamline number. This could be any value that we would like to start from 0 streamline from that on the surface we have a streamline which is equal to 0. So this is C equals 0. And at which is going to infinity, it's equivalent to Y infinite edge of boundary layer. We set that velocity is equal 1, or okay, this F prime is velocity divided by infinite velocity. So it means that on the edge of boundary layer, our infinite velocity would be equal to velocity on the edge of boundary layer. So we set these three boundary conditions, because this is third order differential equation, and solution can be obtained in coordinates of F prime and in coordinates of eta. F prime is dimensionless velocity and eta is dimensionless distance. Okay, distance velocity. So we see profile of boundary layer. We find the solution of profile of boundary layer. Such equation 15 nowadays can be easily solved with any simplest numerical method. For example, in MATLAB, if you put this equation with these boundary conditions, you will receive profile which you see on figure 2. Why it's so important? This is important because profile of this boundary layer is identical for any cross section. It's so-called self-similar solution. What does it mean? We have solution shown, for example, on equation 18.3 for two different sections, just transforming coordinates from eta and F prime to Y and V coordinates. We obtain profile corresponding to different stations. So finding one-time solution or finding solution just once, we can calculate profile of boundary layer for infinite number of locations in X and in Y direction. Based on this solution of Blasius equation, since we can analyze all boundary layer for any station, any cross section, and any distance from the wall, we can analytically obtain, not analytically, analyzing this numerical solution, we analytically can obtain friction coefficient, which is given on the top formula here. This is for b-dimensional flow. We can obtain also friction coefficient for three-dimensional flow over a plate, three-dimensional plate. Okay, plate which has, plate has 2 dimensions, but flow is 3-dimensional. We analytically can calculate thickness of boundary layer for laminar flow, which I think you remember if you studied well aerodynamics. At the very beginning of aerodynamics in introduction chapter, we had these equations as estimation of thickness of boundary layer, where we calculated profile of boundary layer. Also analytically, we can obtain displacement thickness. So if flow is laminar, we know how streamline will move in outside of this boundary layer in this regime, and we know analytical estimation of momentum displacement thickness. A lot of information. Once we obtain Blasius solution, we can have all these integral parameters as friction coefficient, b-dimensional, three-dimensional, we can get also thickness of boundary layer, which is also a sort of integral value, right? Once we integrate velocity profiles. Very nice, very good result of just the transformation of flow equations. Analytically, we can obtain a lot of information, and this is very close to real flow. For compressible flow, it's possible to provide similar procedure, but with some adjustments. Main adjustment for compressible flow with respect to Blasius solution would be that density is not constant anymore, so we need to use one more equation and we need to use one more parameter, which is density. Here is the equation system for boundary layer, which we saw on previous chapter. Equation 31, continuity. 32, 33, momentum in X and Y direction. Equation 34 is the energy equation. Transformation of this equation is done by introducing new parameters. On X direction, it will be also eta function. Now eta function would be a product of density, viscosity, coefficient, velocity outside of boundary layer, all this with E subscript multiplied by X coordinate. So it will, this parameter will explain to us dimensionless, coordinate on X direction, not dimensional, sorry. And eta function, the second one, will present to us a combination between X and Y direction, but mostly on Y direction. Okay, because X is in square root and Y is in a linear dimension, so it represents more Y direction than X direction, but it's same as for previous approach. For Blasius solution is a combination between two dimensions. Same as for Blasius solution, we have definition of f prime as a ratio of velocities, and to take into account change of density, let's say using energy equation, we are introducing another independent parameter, which is g function. This function represents to us enthalpy ratio. So g function will also be dimensionless. Once we write f prime function or define f prime function and the g function, we can transform our equation system and obtain equation 42 and 43. This transformation is very large, so I think even Anderson does not show this transformation, but if you are quite interested how it's done, I think we can find reference on this transformation from boundary layer equations to equation 42 and 43. Equation 42 and 43 are combination of momentum, energy, and continuity equations. We can see on equation 42 is present also other parameters, density here, right? Viscosity, dynamic viscosity. These parameters here, density and viscosity, they are constant values, but on the numerator of this fraction, they are functions. And on second equation, we also have functions of density, viscosity, constant divided by constant values, also by Prandtl number. And here starts to be present g function, ratio of enthalpy, g function with the first derivative of g function. Okay, and other combinations. All other parameters, I hope you understand. what they mean: velocity, enthalpy, density, and dynamic viscosity. These equations can be solved also numerically, same as Blasius equation. To solve them, we set up boundary conditions on the wall at equals 0. We say that the streamline function and velocity would be equals 0, first equation here, or first condition. And on the wall, we set enthalpy on the wall, or temperature on the wall. It's equivalent as we set, for example, temperature on the wall. Enthalpy and temperature are related. Probably you remember, right, that enthalpy is Cp multiplied by temperature. So it's quite obvious linear relation. Cp is considered constant in this calculation. And for infinite eta, flow outside or on the edge of boundary condition, we said that velocity would be equal to external velocity and temperature would be equal to external temperature when enthalpy at a specific point would be equal to the enthalpy on the edge of boundary layer. Two equations. So as solution, we have a function of two independent parameters. These parameters would be Mach number and distance. Solutions of presented equation system is shown on figure 4, 5, 6, and 7. I just combined them to look better on just on one screen. Let's take a look closer on this solution. Since there are two parameters, we plot not just for velocity and size coordinate, but we also plot in for temperature and size. So there is a velocity boundary layer and there is thermal boundary layer. Velocity boundary layer is figure 4 and 6 on the left side of this screen. You can see here profiles of boundary layer. For small value of Mach number, this is Mach 0. Theoretically, here we see that thickness of boundary layer would be very small. Right. Once we increase flow velocity, external flow velocity, boundary layer will also grow for a very high supersonic or hypersonic Mach number, Mach 6, Mach 8, 12. Boundary layer thickness theoretically is quite significant. Right. Higher is Mach number, bigger is the thickness of boundary layer. And this figure 4 and 6, they are different for different boundary conditions on temperature. Since we are solving system for different initial temperature or boundary temperature, we will have different solution. Figure 4 is for insulated plate, where temperature on the wall is not influencing on distribution on temperature outside. And figure 6 is when we have a cold plate. So temperature of the wall is smaller or significantly smaller than temperature of the flow. So there is heat transfer from flow inside the wall. We see that in such case, it will be different thickness of boundary layer, significantly different. Okay, let's take one value, for example. Okay, this I like more, this in the middle for Mach 8. We see that thickness would be close to 10 for cold plate, and for case of insulated plate, this thickness would be, oh, sorry, it transforms to a line automatically. I will try to do it faster so it will not transform. Thickness is more than 20, maybe 25, 30, more than 2 times different with respect to cold plate. So depending on which flow properties or which thermal conditions we create on the surface of the wall, boundary layer can significantly change for compressible flow. For incompressible flow, it could be different. We know that it will also only impact on viscosity value, but inside compressible flow, it will be even more significant influence. On the right side of screen, we can see temperature profiles for insulated plate. It's figure 5, where temperature on the plate will not impact on flow conditions. We see that in such case, temperature profile is normal or perpendicular to wall direction. So we see that it's a 0 temperature gradient. And on figure 7 is a cold plate. So we start from very low temperature on the wall. Off point starts from 0 position and then increasing due to temperature is increasing due to transformation of energy from velocity to thermal energy. Higher is Mach number, bigger amount of energy is transformed from flow to or from velocity to temperature. Thermal and velocity boundary layer. Also comparing sizes, we see that for thermal boundary layer, thickness is different from velocity boundary layer. For some cases it's bigger, for another cases it's smaller, but I think in general thermal boundary layer is always thicker than the velocity one. Okay, that's it. Distribution of friction drag with respect to different type of boundary condition is represented on figure 8 for a diabatic wall and for okay, this is same temperature as external temperature and the diabatic wall where temperature gradient is equal to 0. We can calculate. For compressible flow, it becomes extremely hard to estimate analytical functions. So equations 44 and 45 are different for different flow condition function f and g. Here, they cannot be found analytically because flow is compressible and flow is complex. Sorry, my cell phone. Okay, I would like to talk a bit about stagnation point and aerodynamic heating. On the stagnation point, having that solution from our previous discussion, we can estimate heating by heating of the wall, at least on stagnation point, by adopting same strategy or same model that is used to obtain Blasius solution for incompressible and especially compressible flow. We also provide transformation of coordinates and apply this transformation to equations of boundary layer for p-dimensional case. We can obtain such function 63 representing to us relation between flow. It's 63 and 64, two different equations in a system, right? And applying boundary conditions for cylinder, we can obtain analytically heat flux on stagnation point, as you can see on equation 65. I think it was, no, 63 and 64, and for cylinder obtain relation 65. And for cylinder equation is 68 and 69 to solve velocity and thermal boundary layer on this cylinder. Such process also can be provided for simple case. I think that the previous one is missing some information. I think some solution was obtained for sphere, but now I cannot find where is this part of sphere. You can find definitely it in 6th edition of the book. One important conclusion on application of boundary layer equations on spherical or cylindrical bodies is that heat flux on these bodies would depend on or would be proportional or reverse proportional to square root of radius of this body. This is the answer why small objects cannot re-enter from space and they will burn, because heat flux on small body would be increasing accordingly to decrease of size of the body. This is why only big re-entry capsule can be returned from space. As a nice result, practical result from application of boundary layer theory to compressible flow. Okay, for arbitrary bodies, same method can be applied. In such case, equation would be extremely complex. It will be still ordinary differential equation system, but okay, it will have some part of partial derivative for pressure, just for momentum equation. Okay, and can be solved. To solve, need to set up similar boundary conditions as we saw before, zero velocity on the wall and known temperature, or adiabatic wall conditions on the wall. And at the edge of boundary layer, we set that velocity would be equal to external velocity. Such equation system can be solved by applying finite difference method, since it has partial derivative. It cannot be just integration by Runge-Kutta method. We need to apply finite difference method where derivatives would be approximated on the mesh according to equations presented on equation 87 and 88. Right, the rearward difference and the central difference, for example, very similar to the equations you already saw on one of the previous chapters when we talk about methods of solution of flow equations. And then once all these approximations are done, here Anderson presents the step-by-step method of calculation. So solution will be started from a leading edge or from flow with maximum velocity or at stagnation point, and then would go to downstream station, or according to flow direction would be obtained the profile of velocity, and then at the edge of boundary layer calculation will finish. Okay, some additional considerations how to obtain with the greater accuracy derivative of velocity and temperature on the wall. These are important to calculate shear stresses and thermal loads, heat fluxes on the wall. Equation 91 and 92 gives to us more precise than first order approximation relations. So once we know 3 points in space inside the flow, for example, this is the wall. This is our wall point where we are interested to calculate gradient of velocity or gradient of temperature, no matter. This is point 1, point 2, and point 3. They all are having same distance one from another. Delta y, delta y, delta y everywhere. So this distance between points is equal. If we have these 3 points, then gradient of velocity and gradient of temperature could be precisely calculated according to formula 91 and 92. These estimations are important for calculation of shear stress and calculation of total drag on the wall and calculation of heat flux on the from flow to body. Okay, some solutions showing standard number, skin friction coefficient for specific body called hyperboloid. It's just an example of application of these flow equations that allows to obtain a thermal boundary layer and velocity boundary layer by different methods, including this numerical simulation. And that's the end of part 18. I'm wondered where is temperature reference method. So probably next time I will add here, because at the end of chapter 18 there is also temperature reference method. Here, unfortunately, I do not see. It's very simple and very fast to explain. Probably we can do it on our next meeting. I will adjust the presentation for next class and you can see this topic as well. Have a nice week and see you next time. Thank you for participation today.